Hello and welcome to 20th lecture of the course on corrosion, environmental degradation and surface engineering. In this lecture, we are going to continue on a non-destructive testing. It is a part 3 and we will try to cover main two techniques. One is a acoustic emission technique, another one is stress strain DIC testing. So, what is shown in this slide, it says very clearly green color, visual inspection is clear, ultrasonic testing we have covered, radiography we have done, magnetic particle, eddy current, liquid penetration test have been covered also. Now, thermographic testing was covered in a previous lecture, but in this lecture I also want to continue and want to give one or two examples. And after that we will be covering acoustic emission and stress strain DIC testing. Now, let us start with thermographic testing. We give a lot of importance to this testing, reason being is kind of surface capturing, or maybe say even within a surface or below surface and volume we can capture many thermographic images or maybe say mapping. And we know very well that the temperature is above absolute 0 value or maybe say absolute 0, the Kelvin 0 Kelvin, then every body will emit emissions. So, that is why we want to cover maybe in 2 slides. So, what we started in previous lecture. What is in this case is mentioned that is a promising technology, this TT or we say another active infrared thermography is a promising technology because of the high efficiency. So, this high efficiency is kind of a relative term. What we really require, we want much faster results, and then we take some image, thermographic image, and we want to interpret much faster. So, the actual maybe the necessary action can be done. So, from in situ point of view, when really on the field we want to capture the images and get immediately the results, from that point of view this thermography testing is very good. And in fact, major advantage happens when there is a corrosion in a metallic shells, which happens in a number of places like overhead the tanks, pipes, containers. These are the sources, or these are the metallic shell where the corrosion often occur, and then thermographic images or maybe say testing will be very useful to capture immediately those images and then indicate that there is a corrosion in this kind of casings. So, that is why it is mentioned that corrosion in metallic shells such as above ground tank, which we are not able to reach easily, pipes which are submerged, or maybe we can't open it easily, and the container maybe storage container something like that can be detected using portable experimental infrared thermographic non-destructive testing. So, this is a major advantage. One thing is that it can be portable, very small cameras, and then we capture, and if there is some sort of a mapping, thermal mapping, and it can be converted to the visual photographs kind of thing, then it will be very useful. Now, one more point comes why it is more important. It says the infrared inspection equipments is a cost effective compared to the ultrasonic thickness gauges, right. So, whenever the cost comparison comes, UT will be treated as a bit costlier compared to the infrared. Of course, it depends on what kind of sensors we are choosing, what kind of cameras we are choosing. I am just giving data on average, it is not that it will be always, right. Somebody has brought a much better camera and somebody is using a sensor which is relatively cheaper compared to the best sensors available. Naturally, in that situation UT will be slightly cheaper. So, however, we are talking about the average values. In this case, we say the IR inspection equipment is more cost effective than ultrasonic thickness gauging. Particularly as I above mentioned like a above ground tank or pipes or container, particularly for the metal casing required to store or transport petroleum, the product which is really required in petroleum industry or power generation industries. So, these are the two major important thing. One is the portable and then there is a cost effective. That is why the thermographic testing is a very good option. Let us take a couple of examples as I mentioned. In earlier cases I did not mention about the heat source, and recent findings are indicating that if there is a good heat source available, and the camera is one point, but if the heat source is also available and it is really impinging a light directly on a test object that has been shown using the yellow color, the test object, that then whatever the emission from object in response of the light the image on that will give a better results, and those images either the camera has capacity to store those images or it can be stored also on a computer. So, this subsequently we can do like a reduction in a noise, enhancement of the images, getting a better results, something like that. So, that is what we have seen. IR thermograph can be obtained after doing a necessary processing on a computer. If camera has inbuilt processor and which is very good, a costly camera, then it is okay, otherwise we should do on a either on a laptop or computer or whichever is available to us. So, this is overall has been shown, and then we have taken example from one of the reference which was published in 2020. They did this experimental testing and that particularly on corrosion related coating, corrosion related testing. So, what they use powerful LED source that as a heat source they have used, then in the imager or maybe say camera, then computer and then reference sample, because thermographic images need to be compared with the references also. So, we will not know otherwise, and again this is a relative comparison, relative compared to the some sample which has been given. So, let us take example. In this case, if this is a tank which I want to keep as a reference, I can fill it with the water, I can fill it with the sand, I can fill it with the only air is empty. So, I can really detect in all three cases what will be the results. So, in this situation another point has come that whenever the test object, because emissivity will increase if we do a black paint on that or we blacken that objective piece. So, that is why this is written here that to improve absorption of the thermal radiation, sample surface are generally black painted. It can be any kind of paint. In this reference they use a matte acrylic dye, and as I mentioned that they use a powerful LED the heat source, and then they kept a very low frequency as such. Another one, the distance of the heat source, distance of the camera, these are also the parameter which really affects. That is why we required experience, and after the experience we can really figure out what will be the really appropriate distance between camera and object, and then camera and the heat source. So, that what they have written here, the LED heater was kept around 0.4 meter away from a reference sample. Another one, this camera was kept around 1.1 meter away from a sample to record the temperature, to map the temperature. So, these are the points which are really required. What will be the distance of the heat source from object, and what will be the distance of camera from a test object. Maybe the variation and then we can figure out at some places, some angle it is giving far better results compared to others. So, that will be the kind of iterative procedure and really required the few iterations to come up with the right results. So, this is what they have shown, and then they presented the number of thermographic images which I am trying to show. They use this tank thickness around 2 mm, 4 mm, 6 mm and 8 mm. So, they vary the thickness of this tank, and then they took some images. So, initially the raw images something the signal to noise ratio was 5.6, but after processing they increased to the 23.1. So, this is a post processing is important. Thermographic images alone will not be giving very good sharp images, So, that is why they have shown that 5.6 to 23.1. Similarly, in for thickness 4 mm, they got from camera 4.7 as a signal to noise ratio, but they improved to the 9.2 after doing the processing, image analysis and other processing. And then at the length maybe say when the thickness is a 6 mm, they got a much lesser signal to noise ratio, that is 1.9, and then they do post processing, they increased this to 4.6, and the length outside the thickness 8 mm, they found signal to noise ratio very low, 1.7, and that was improved. So, overall I can say that the thickness of the sample if it is reduced, it gives a very high signal to noise ratio, it is also important. So, that is why they have done, and then we are showing here that this thermal waves versus they also compared thermal waves continuous source and then pulse pulse waves, and then they found that this TD the NDT was already in the name, we are giving the non-destructive testing, but T has been added in this case, that is a thermographic non-destructive testing. So, TND has been mentioned here, the results of thermal wave TND of the reference sample. So, this is related to thermal waves, and while on this side in this figure what they are showing something like a pulse thermographic non-destructive testing. So, that comparison has been shown. The same thing in this case also, signal noise ratio 3.2, and then it can be improved to the 9.7, and then in this case length in the thickness 4 mm 6.8 signal ratio can be improved, and that is what has been shown, and finally in this manner. And then what they try to conclude that if we give a pulse thermal waves, or maybe say it is not continuous and then in the pulse mode, it will give a better results as such. Now, that has been mentioned here that due to the shorter observation, because there is a pulse we are sending and we are closing and we are sending the temperature or heat to the object, and then we are closing it. So, due to the shorter observation interval and reduction of the heat dispersion. So, heat dispersion also reduces, and they concluded the pulse TND TNDT will be better option, or it will give a crisper defect images. Another one comes that there are so many parameters in this. So, how do we go ahead with that? Because there is a signal to noise ratio is 1, there is a temperature, and then what is we need to really predict with the temperature mapping what kind of crack, whether the surface crack or maybe the subsurface crack or maybe the volumetric crack or something like that. So, there are many parameters. So, in that they added the mathematical model is something like what we call as a principal component analysis, is also popular in the machine learning algorithms. So, they utilize that kind of PCA to detect what is really good, and so that they can predict the results, and based on that the PCA results only they concluded that this pulse T and TNDT will be a better option. So, if I want to really express what is really PCA, I can say that PCA is a principal component analysis. It has a number of application, particularly when the dimensional data are many, when we have too many variables and then we do not have a definite relation available with us. So, in that situation PCA will be a better option, because that the method try to figure out some sort of relation and then maybe make a lesser number of equation, even though we have too many variables, but what will be the more important variables which are impacting the results that can be extracted using the PCA. So, this is I can say that goal of principal component analysis is to reduce many dependent variable to manageable subset. Maybe only few variables can be given as an independent variable, even though there are many dependent variables and we do not have a complete definite relation available. So, when we do this, and that is why many times we say these are the data driven approaches, and then particularly surface engineering is more governed with a data driven approach. That is why the PCA plays an important role, and I say that I can make any linear combination of the dependent variables, or depending the what kind of curve fit method has been used, or maybe the additional advanced method has been utilized, which can give some sort of combination, and then lesser number of equations, and then more the control parameters. We will know that how do we really control the signal to noise ratio, and then how do we interpret what kind of cracks or what kind of corrosion mechanisms are happening, and what is the depth of the corrosion when we use a PCA. So, these are the very important things from that. So, again if I want to really say in slightly different manner, I can say the features can be extracted and analyzed using the principal component analysis, which could add identifying the trend with a corrosion. So, if I want to really understand the corrosion, PCA will be very useful. So, it is not only the PCA can be used only for thermographic testing, it can be used for other things also. That is the learning the PCA will be important for us. And as I say the number of things, as I say that if I have a relation, I can figure out what will be the corrosion rate, and then how it is really progressing towards a thickness, and then how it is really going to impact environment, or environment is going to impact corrosion. These kind of the things can be utilized. That means we do lesser number of tests, but we will be having a better and better results, and then we do not have to do too many tests to just the results. And again I am mentioning that we do not have a definite relation available. If there is a definite relation available, then I do not really require a PCA. When there is no definite relation available and we want to extract the relation, then PCA will be very helpful to us. Now, one more point comes that we have talked about the IR emission, but there is another kind of emission what we call acoustic emission. And what is acoustic emission? We say this method is used to identify and assess how material responds to stress. So, whenever the material is loaded, it will be subjected to stress or strain, and then if we are able to correlate some sort of emission which is happening coming out of the object in response to the stress, and if we are able to diagnose that kind of emission, then it will be a very useful NDT technique for us, and that is what we are going to cover this technique in next 3 to 4 slides. So, let us say acoustic emission the non-destructive testing, and what we say that this is basically the acoustic emission is kind of elastic or transient elastic waves, and then which can be produced by the localized sources or maybe in a material. What are the localized sources? It is something like a flaw or maybe crack or some sort of irregularity on the surface, or some sort of the structural integrity fault, or maybe we want to really assess the complete progression of the damage. Maybe the crack has been initiated and crack is progressing, and that complete tracking can be done using the acoustic emission NDT. That is possible, and it will be very useful particularly whenever we require 24/7 observation. And if we want really 24/7 observation, I believe the acoustic emission is one of the very powerful tool or one of the powerful testing method in the situation. So, this is what we say that it paves way for the round the clock monitoring. That is what I mentioned, the 24/7, and then it will yield useful data. So, which can be interpreted, and then not only short term, but also on a long term. That means, if we are able to develop a good models and we are able to predict that now maybe the corrosion rate is this much, after 10 hours, after 100 hours, after 1000 hours, it will go to this level, and that time we should shut down the plant for the overhauling. So, those things are possible when we go ahead with the acoustic emission NDT. Now, another one what we are saying in this situation, that the sensor or transducer whichever we are available to us need to be attached to the surface. Because the sensor plays an important role. If it is attached to the surface or attached to the material, and then it will generate an acoustic emission, and then we need to really capture those emission. We need to do analysis. It can be time analysis, it can be frequency analysis, and we should have a database to interpret those results. If we do not have a database, then we need to really do some sort of a lab test in our lab. If database is available, very good. However, many times we buy this kind of complete equipments, and the company who is supplying this equipment, they have complete database, they have their own library, and then they predict what is the kind of the failure we are really getting into the surface. So, what we see in this case, when the material is subjected to strain or deformation or straight, whatever you say, then elastic waves of high frequencies are produced. So, main thing, when the material is subjected to strain or deformation, elastic waves of the high frequency will be produced, and these sensors can detect those things, because the sensors are attached on the surface itself, very close to the surface, there is no gap, and then whatever the high frequency signals where they are getting, or maybe elastic waves they are getting, they can really capture, they can record it, and then when it is detected, analyzed, then we can figure out what kind of the problems are there. As I mentioned that we need to have a database to say, okay, maybe the 10 Hz frequency means what, 10 Hz frequency, this much amplitude means what, if the amplitude increases what kind of fault will be there, or maybe we are continuously doing the kind of a time analysis, then we can say, yeah, now initially crack was this much smaller, now the crack is continuously increasing, and then we need to really give a kind of a signal for the overhauling or the maintenance. So, it is a very important tool from maintenance point of view, from overhauling point of view, and giving a valid advance information the material is not behaving. So, again I am using the word, it is not absolute method, it is a relative method, it is a follows a trend analysis, and if we want this to be an absolute, then we need to really have a very strong database with us and very clear cut interpretation, and then maybe advanced analysis technique along with us. Now, this is I am trying to cover one example which was published in 2005, and then this is related to gear, and as I mentioned that as we are covering the acoustic emission technique. So, they have used a curve this gear setup that has been shown in figure 1. It says clearly test rig gearbox in a back to back arrangement. What is the meaning of back to back arrangement? We use two identical in the pairs, one left hand side, one right hand side, so that we can cancel many noise related things. So, they use two identical oil bath lubricated gearbox, and then they just to do accelerated the test, they use a very rough gear, so that they can get a very good response to that. And then another thing is that they seeded the faults, so that they can really calibrate the sensor and the technique, they can establish a technique where we are intentionally giving a fault to the gear surface. So, they have introduced a pit, they also introduced the flying related at the edge, and they have created a fault on that. So, that is what they have done, and of course, this whole setup was run for the 3 different test setting. That is what they use, a 3 torque setting. One is as a no load at all, no power transmission, only the rotation, and then second case they operated as a 55 Newton meter, that is a torque value, and after that they have a double that value, that is a 100 Newton meter, 110 Newton meter, and the whole setup was run with a AC 3-phase AC motor, and the power has been given as a 1.1 kilowatt, and they operated at a 745 rpm. So, this is basically to predict what kind of frequency we will be getting, what kind of the signal denoising we require for that purpose. And the sensor location, they have shown the 2 locations. You can see here the gear has been shown, but gear has some sort of casing. This casing has been there, and then they have put a sensor on that the casing. So, that means there is a rotation of the casing, and the rotation of casing the sensor cannot be fixed easily. So, they use a slip ring arrangement, and slip ring arrangement is a special arrangement particularly for rotating the sensors. And then another one they have used a sensor on a bearing housing. Bearing housing are generally stationary, and then that is why they use this sensor on a bearing housing. So, what is the advantage, what is the disadvantage? Mostly we do not have to go with slip ring arrangement, which is slightly costlier and maybe will wear out very fast, and we need to replace it frequently. While coming to the bearing housing, it is static, it does not move, rotate. So, that is why it is really the sensor can be easily fixed on that. However, this bearing casing is slightly away from the damage. So, there is a possibility of the attenuation of the fault. Maybe the fault is on higher side, but we are not able to get out the bearing when the sensor is attached to the bearing housing, or maybe we are getting alarm on an extreme cases, not at the initial stages. Just to differentiate that is why they have used the 2 different sensors, so that they can compare these 2 sensors. So, what is mentioned here, acoustic emission sensors, with every sensor will have some sort of linear behavior in some frequency range, and that is why they have selected 100 kilowatts to 1 megahertz. In this range, this acoustic emission sensor will give a kind of a linear range, and that can be captured easily. Of course, there will be again calibration constant every time whenever we use this kind of sensor, we need to be recalibrated and then do the necessary thing. As I mentioned here, that they use this one sensor on pinion, which is on the driver, which drives gear, and the pinion had a 49 teeth. For us immediately is not really required, but when we do the match frequency, we do the analysis of frequency, then this kind of data will be required. However, as I mentioned, they use acoustic emission sensor on rotating component, so that requires a slip arrangement, so that the rotation is happening and then the signals are getting transmitted to a stationary device. That is what they have used it. And then this is what I mentioned, the slip ring arrangement with a pre-amplifier, because every sensor required a pre-amplification or maybe the post processing. We need to really remove the noise. Noise will be coming from the surrounding. Sometimes people use some sort of isolation devices, so the surrounding noise should not come. However, it depends what kind of a noise level comes, and then what kind of a cost we can really afford to spend on this kind of setup. Now, as I mentioned, the two kind of the faults they really create it. It is not that they are directly diagnosing, they are creating, so they know exactly where is the fault, and then so that whatever the algorithm they make, that will be easy to predict the failure if we are able to match. Of course, in reality faults will be available or may will be created during the process, then it will be naturally there will be little more difficult to diagnose compared to the seeded fault or intentionally made faults, and they are able to see here the fault also. And so, this is what has been shown. Now, if I express in my word, I say these authors operated a gearbox initially, because in the beginning of the lectures I mentioned that there is a something like a wear mechanism, and wear mechanism will always happen if there is a relative motion and there is a load. So, in this gear pair they are applying a relative motion and there is a load, naturally there will be some sort of a wear. And initial one, which we call as a running in wear, where the two surfaces try to remove the surface asperities, and that is what the running in, where the overall wear weight will be very high, and that was indicated in our lecture on the bathtub curve. We say initially wear rate will be high, and maybe after the running in period wear rate will turn out to be kind of a very low wear to the ultra mild wear kind of thing. So, in this case authors run this setup for the 15 hours and then they treated this 15 hours as a running in period. Then another thing that what they felt that there is a possibility of the background noise, but background noise will be there when there is a load and there is no load. So, just to differentiate that, they what they did, initially all the readings were taken and then without defect, and then initially with load, without load, that is what a 0. Then they run experimental setup for the 30 minutes, they collected the data, and then again they kept equipment for the stationary condition for some time. Again they operated this at the 55 Newton meter, then they operated at the 110 Newton meter. So, initially without defect and after that with a defect, so that overall results can be compared. As I mentioned that acoustic emission is a good the comparison purpose or relative performance compared to the absolute value, that is what they did. One set without load, then 55 Newton load, then 110 Newton load, and similar set was repeated when the faults were seeded, and there were two type of the faults. So, overall 9 tests means minimum is required. However, we know that single test will not give reliable results because everything is statistical. So, naturally it has to be operated couple of times, it is not a one time or two times, it need maybe more number of times. As I mentioned that they seeded the fault on the surface, so that this pit which was generated on the gear teeth, it was really the near the pitch line, and the diameter they kept as a 1 mm on the surface. However, when come to the fault on the gear addendum side, So, they kept a kind of rectangular fault that was around 12 mm by 3 mm, the kind of a fault there. So, there is a significantly high, it can be easily detected even with the naked eyes, but they use acoustic emission to figure out what is really happening, and then they kept something like a sampling frequency around 10 megahertz. So, they whatever the signal they were capturing, so that they use a high frequency, so that the signals can be captured and analyzed properly. Now, I am trying to show the results what they have done. You can see that this figure, this is all raw figure, not without post processing. And then initially, as I mentioned, there are two faults in this case. They are showing the 1 mm fault which was on the pitch line, and then initial signal is no load. So, you can see even the no load case that there are some sort of signals coming. Now, with the 55 Newton meter, this signal amplitude has gone slightly upper, and then the more distributed across in the time span. Even as I say, this is the transient behavior. Other one is a 110 Newton meter. So, that the amplitude again further has gone on the higher side compared to the 55 Newton, and then this has been indicated in this. So, time says something, that something is wrong, but when we convert to the frequency domain and then we segregate in a different band, they found the fault is in the higher side in the C region, and exactly whatever they generated a fault, they were able to capture the C and then this fault easily, and then they see that magnitude or RMS value RMS value of the signals is increasing, and in this value in this way, and then there is a comparison also that even no load, this is the data, and then 55 Newton and then 110 Newton. And this is what they say, the central lesion C where the seeded defect was inserted shows the greatest RMS value for pitch line defect which was seeded to the surface. Now, to compare both the sensors, which one sensor operated on the mounted on the bearing casing, another operated on the mounted on the gear on the sleeve. That has been shown that when the sensor which was mounted on the gear sleeve, another sensor which was mounted on the bearing casing. Now, they are able to show that there is a huge attenuation. You can see here the values which they are showing is far lower compared to the what value has been shown on the gear. So, that what they indicated, that mounting the acoustic emission sensor on the bearings is not really giving good results. It will have a slightly versus side signal to noise ratio, and we need to really very high which is that the post processing to really extract the some fault. While coming to the sensor which is mounted on the gear sleeve, it will be slightly costlier because we need to use a slip ring arrangement along with the sensor. So, that is slightly costlier, but there you can find that it is really giving very good response, and they found the location 44 dB attenuation at one location and 26 dB attenuation other location. So, what they concluded that as the sensor is close to the fault, it will be always better, whether it is rotating or stationary, but better you keep there. So, what we as I mentioned earlier, that we need to also detect the sensor the fault which is created or maybe which generated immediately, so that we should know the root cause failure, and that is why the AE will be more useful for the continuous monitoring. It is a continuous monitoring of AE sensor on a bearing case shows loss of acoustic emission which is compared to the sensor which is connected to the gear mesh. So, that is what we indicate, this has been indicated that even the same technique, but a different location will really impact the result, will give a different kind of results. So, and then this is what location what they mentioned that they need to blame, and then the bearing location is a need to be blamed, and then another thing which they mentioned that the ball and rollers, because the bearings which we use, they are not fully complemented. Fully complemented means like not every space has been obtained and occupied by the balls. Many times we have a separation between balls, like we are using 9 balls or maybe 11 balls or 12 balls. Naturally, there will be some gap, or maybe the rollers there will be some gap. So, when the ball is directly under load, that time signal is on the higher side, when and then after maybe 10 degree rotation and 15 degree rotation, another ball will come under maximum load, then again will be good sharp signals. So, that is what they are mentioning, that because the bearing which we are using, that has some sort of a discontinuity. It is not a complete the bearing has been have all the balls or rollers. That is why we are getting a lot of attenuation of the signals. If however, we keep fully complemented like a needle roller bearings and all, we may get a better response. In the situation we can use a sensor on a bearing housing. So, if you fully complemented bearings, then we can go ahead, as I give an example of needle roller bearing, where almost every space is been circumferential space is been occupied by needle rollers, but in the bigger side rollers or the balls, we generally have a separation. Because that has a sufficient load and then sufficient static load as well as a dynamic load. So, that is why in the situation either we change a bearing or change a sensor location, that was predicted, and it really affect the results. Now, I am trying to cover another example also, which is connected to the corrosion testing, and then we are using the acoustic emission. Now, here the importance is given to this testing, particularly because we know that corrosion will start, propagate and cause a failure, and that is why they say that this the SEC, which we already have covered, and this has been has come from a reference 2020, and what we are using the word stress corrosion the cracking basically or fracture, and then this stress corrosion cracking always initiation phase will be there, always there will be some sort of surface roughness, there will be some sort of surface and the dent on the surface that can act as an initiation. However, if the material is very good and tough, then there is a possibility that we may not get this kind of fault, or if there is almost zero atmospheric corrosion is not there, and environment is not really corrosive in environment, there is no corrosion as such. So, that again we will get a good results. However, this is what the first case, and if we are observing the signals from scratch, then it is a very important. However, as it comes in the transition phase, and there the sensors really helps a lot, because we will be able to detect how much time will be remaining, so that we can do necessary maintenance or necessary replacement or necessary overhauling. So, this is what they mentioned, particularly for SEC we required acoustic emission. So, it has a very high importance when we want to go ahead the round the clock testing, and then we want all the responses keep coming, and then we get alarm whenever there is a fault is going beyond controllable limits, or well in advance knowledge that what is the status of the fault. So, this has been mentioned that the leading cause of the failure in various industrial sectors, the stress corrosion cracking necessitate accurate production of activation and propagation. So, even they are saying that even if there is an activation or a start of a crack, or maybe as I mentioned that cracks will be there, irregularities will be there on a surface, but are they noticeable, are they sufficient to increase in its size? If they are not sufficient in increase in its size, and there is some need of the energy, additional corrosion mechanism of something, then we do not have to worry. But if it is started, they are getting some sort of activation energy, and it started to progress on, it will be subsequently propagated also. So, that is where we require this kind of testing, and as I mentioned, the in situ monitoring of transition from initiation to the propagation is very helpful. So, this is a major advantage of acoustic emission for the number of industrial sectors or industrial units. As I mentioned, this has been taken from this reference, and then another thing is that they need to be carefully positioned close to the test material, as I mentioned clearly. Now, in this case particularly they wanted to use for the UTM, and in a UTM itself you can see that the dog bone sample they have made, and they have kept a sensor 1, sensor 2, so that the complete reading keep coming. So, how the crack is initiating or becoming activated or become in active position, and then how it is propagating on a surface, that can be detected using acoustic emission. So, this is what advantage, and they try, and I am trying to show the results. Now, what they say in case of the corrosion, there are many mechanisms. Now, this is what we say, that ongoing corrosion processes, it can be uniform corrosion or generalized corrosion. It can be pitting or crevice corrosion, and these are the localized faults, or maybe in the extreme cases where the three modes of the failure work together, that is what we call a stress corrosion cracking. And it can, another term comes to something like there is a tribology is also happening, and the corrosion also happening, and the fatigue phenomena is happening, and corrosion is also happening. So, any case of the corrosion process, in the situation acoustic emission, the unit will be more important, and that is why another point comes, we need to have a very good strong research, or maybe the data available, or maybe the we say that complete database, or whatever the response I am getting for A, is it corresponding to the uniform corrosion, is corresponding to the pitting, is it corresponding to the crevices corrosion. So, naturally that need to be diagnosed, and that is why there is a need to really focus on that. And as I mentioned, that when you buy sensors and complete unit, that concerned company will have all those units. They must have done lot of research and correlation between the different kind of faults, and then the sensor will be having all related software available. So, that whenever the signal is captured, analyzed, and the software will tell, oh, there is some sort of tribo corrosion, there is some sort of crevice corrosion, or maybe pitting corrosion. So, we get information well in advance. So, this is what been mentioned. Now, what they are doing is something like, if there is a metal dissolution, we know then corrosion, metal really gets converted to iron, and there will be anode action and cathode action. And anode, we know that the metal ion will be released, and of course, electron will be captured at the cathode, and then there is a hydrogen ion will be there, and that will get converted to the hydrogen gas. So, that is what they are mentioning. So, whichever element here that there is a acoustic emission will be there, again the cathode acoustic emission will be there. If there is a thick oxide and there is some sort of cracking in thick oxide, again there will be acoustic emission. So, whatever the corrosion related phenomena we are able to observe, that there is some sort of acoustic emission, and then we need to differentiate between the frequency and amplitude. So, figure out what kind of corrosion mechanism is happening. So, from that point of view, I believe that acoustic emission technique is very good to judge the kind of corrosion, and they are trying to utilize the all ongoing corrosion process can be diagnosed using the acoustic emission. That is what has been mentioned here. Now, that is what we mentioned, the stress assisted corrosion damage mechanism are the sources of acoustic emission, and that has been mentioned. And then we are trying to summarize this: the formation of the hydrogen bubble due to cathodic reaction, initiation and propagation of the crack. Everywhere we are finding that acoustic emission will be there, destruction of the thick film surface coating, even the slip deformation which happens in the plastic duration, or twin deformation, fracture, decohesion means the removal of the from the surface, that also will be there, or if there are some sort of non-metallic inclusions in the surface, then also will cause some sort of a different acoustic emission. Only when we have a sense, when we have a sensor and associate units, that this need to be diagnosed which acoustic emission sense the signal is corresponding to the hydrogen bubble, which is corresponding to the propagation of crack, which is in a proportion to the destruction of the thick surface oxide. So, we need to really detect those, and this paper really also provide some sort of signals. You can see here that there is a one signal here, this is the time domain signal that has been converted to the FFT using FFT to the frequency signal domain signal, and that is coming around 10 kilohertz. This is something like, and then what we say A and B are the diagram related to hydrogen gas evolution. So, this paper indicates that for the hydrogen gas evolution there will be a separate AE waveform, and then the time waveform has been shown and the frequency waveform has also been shown. Now, coming to the C and D, then the time signal has been shown in a C, which is related to the rupture of oxide film which is there on a surface, and we call as a rupture of the passive film, and the D is a kind of a frequency analysis of that. However, if you look at this range is from 0 to 1000 kilohertz, and this range is from 0 to 100 hertz. So, there is only this much difference. and then in the second diagram they have expanded. So, we can see the much more clarity, and third again is from 0 to 1000 kilohertz. So, ranges are more or less and the A and then in this B and F are same, while in case of the D it is expanded. So, to see the what is the variation on the surface. Now, E and F figures are basically to observe that AE waveform corresponding to the metal dissolution. So, in this paper they are trying to analyze that. However, there is an amplitude difference here, we find 0.04, here amplitude is a 0.028, while here is a much lesser amplitude is a coming a 0.007. So, this is almost 1/10 of the other responses. So, that means the rupture of the passive film will have a much lesser response compared to the evolution of the gas, or compared to the the metal dissolution, or maybe the corrosion action, which is a initiation of the corrosion. So, this all the signals or all the values will have always a characteristic frequency, and that is why we required a complete database. What is the characteristic frequency for the S2 liberation, or maybe the breakage of the passive film, or metal dissolution. If we know the characteristic frequency, we can really immediately diagnose that this kind of failure is happening due to the this kind of corrosion, and that has been shown here. The broken film will have a low amplitude peak, and the peak has been shown roughly 50 kilohertz. So, here we can see here 50 to 70 kilohertz something has been shown here. So, it is roughly 50, and then we say the anodic and cathodic hydrogen bubble evolution happens around 50 to 70, but magnitude will be also higher. So, here the magnitude is much smaller, that is why it has been mentioned very clearly that it is a rupture of the passive film, and the magnitude is increased significantly, even though ranges are same, but in that situation it will be the cathodic and anodic reaction which are happening, that has been mentioned. Now, towards this last of the slide of the acoustic emission, they also mentioned that we can do a trend analysis, a time analysis, and they capture the signals like individual signal, something is coming, and like this white dots, and then if the black dot is something like a cumulative damage, and then they are plotting individual instantaneous failure or cumulative failure. You can see that the red line is going from starting almost at the 10 to maybe the 1000 second, and it is continuously increasing. So, almost the 100,000 time it is indicating the rupture stage, and then this is what we say that acoustic emission heat and the heat energy has been continuously increasing from 1000 second to the 1000 second to the 100,000 seconds. This has been shown in this case. That is what we are saying, that is basically is trying to track evolution of the acoustic emission heat energy, that is open circle which has been shown, and I mentioned the cumulative acoustic emission which has been shown as the black dot, and then in the continuous line and the red color line, and this experiment was done on a stainless steel. So, what really comes out, what is the really diagnosis from this is say that change over time in a total acoustic energy, acoustic emission energy, if need to be tracked, and it will really indicate that what kind of failure is going to happen, and if one is a kind of the different kind of failure, and then what is the stage of the failure. Now, if it indicates a stage 3 is like a very high alarm kind of hazardous situation which is coming out. So, that is when we maybe say a high risk zone, stage 3 is a high risk zone, and that is what we say that after the 10,000 zone, the 10,000 cycle, this has initiation of a high risk zone that need to be, if we are able to judge using this kind of acoustic emission testing, that is sufficient for maintenance person to really act on that. And so, what we are saying, recording initiation and initiation of SEC and subsequent crack propagation provide a comprehensive understanding of the damage evaluation. So, basically acoustic emission method is very good if you want to really understand complete mechanism. So, this is important for us. Now, which this is what we have covered. Now, there is another maybe the last NDT technique which we are covering in the course is like a stress strain digital image correlation. So, it is as such not a new technique, what we are saying, instead of putting the sensor like in acoustic emission, we say that a sensor is very near to the damage, where the damage is initiated, will be very good. So, however, if we are putting a sensor on rotating component, what will happen in the situation? There is a possibility of using a sophisticated equipment like a slip grip arrangement, and then blood will also wear out very fast, and we need to change over the time. So, to avoid that, we have a good image capturing and the technologies, and then digitization technologies. If we start capturing the images something like 5 frames per second something, and then we try to analyze and compare what was earlier, now what is happening. So, we can really figure out whether the stress is increasing, stress is decreasing, strain is increasing, strain is decreasing, and then if we are able to correlate strain with a real failure, then it will be a very good technique. So, this is what has been covered in this testing, stress strain digital image correlation testing. What has been shown in this case, if you look at the figure, there is a reference set and then the actual set deform image, and then what they are there will be kind of nodes, or maybe node 1, node 2, node 3, node 4, or maybe many other points in this, whatever depends on how many points we want and what kind of magnification is possible. So, through that, so these are the possible things for us, and then if we track, we will be able to find out what is a new position. So, here it is shown the 2 dots, something like the initial dot has been given as a p value, and then the nomenclature p, and second dot has been given nomenclature q. And if you look at that the deform position, the nomenclature has been given p prime and q prime. So, this is exactly same what we do in a finite element method. Under finite element method, we say that what kind of deformation, and based on that deformation we try to figure out the strain, stress, so those things. So, this is the finite element method, a numerical method. Here we are saying now we will capture the images, and in capture image, if we already have assigned the dots on the surface, we can really track those dots, and by tracking those dots we can really find out the values, we can find out the stress, we can find out the strain. So, same finite element method with the image analysis can be really give much better result, and it becomes a non-destructive technique also. So, this is a relatively new and is still progressing. I believe that there is a lot of future after this technique in this case. So, what we can say, the non-destructive, this is optical because we are capturing the images for measuring the deformation and strain distribution on the surface, specimen and structure. So, again this complete thing is coming on a surface analysis, it is not a subsurface, because the subsurface we will not be able to capture the images, we will not be able to see the deformation. However, if because of the subsurface some failure, if some sort of impression is coming on surface, then can be captured, otherwise this technique will be only for the surface. Now, in this digital image correlation, the DIC it basically captures a series of images. It is not a one image, two image, it can be many images, and then it captures the different stage, the deformation states covering the entire surface. So, the way we say the thermographic images, that whole surface gets captured easily, and that is why that is very good. So, in this case also the whole surface gets captured, because we are capturing number of images and whole the surface. So, we are not just concentrating only one place, like a UT, you need to keep a sensor near to that, while in this case the whole surface can be captured. So, sensors will not be really required very near to the crack, it can be slightly away, and then we need to have a good cameras or good analysis software. So, what we are seeing in this case, advanced image processing algorithms are applied to the images to detect and interpret. So, detection is a one thing, other one is interpretation. So, that was again the software plays an important role, understanding science will play an important role, and then we really required a few iterations, or maybe we required a good database and few iterations for to match for our own situation or our own system where the failures are happening. So, DIC is a advantage basically where the surface itself is irregular, or surface is going with the too much expansion or compression. So, wherever there is a complex shape comes, complex surfaces comes, then we can go ahead the DIC, and then it has advantages compared to the traditional sensors which we have covered in earlier few technique. And then as I mentioned, it covers a complete surface, it not only the localized one, but complete surface. So, that is why it is important. Sensors which are difficult to mount on the complex surfaces, then images will be better option compared to those sensors. Now, digital DIC, as I say, the digital image correlation relies on a matching points. That is what has been shown here, that whatever the point, in this case P and P prime. So, there is a comparison. I can compare P with a P prime. What is the difference between the values is coming? What kind of transformation matrix need to be used, because we are going to cover the 3D x, y, z, all 3 parameters. However, in this case we are showing only the 2 x0 and y0, but we can compare up to 3D also. So, in this case the matching of the surface, and then before and after deformation, and before deformation what was the status, after deformation what is the status. So, again it is a relative comparison, and then it is not absolute, it is relatively we can figure out what kind of deformation is really happening, and whether it is progressing to much faster pace and quicker compared to the other maybe surface or other loading condition, or maybe in corrosion cases. So, for that purpose we say the subset of digital images are matched as a specimen moves and the deforms. So, we really require many images. Comparison is a computationally intensive, but we know that in computational power is continuously increasing. So, it is possible and do a lot of post processing. We can really do the noise, the removal of noise much easier in images compared to the data. So, that is very important, and that is why as I say that as science is increasing and progressing continuously, as a machine learning is increasing and utilized more and more, artificial intelligence has been utilized more and more. So, this method will be useful more and more. Now, how do we compare strain? That has been shown a 3-dimensional up here, XYZ, P1, P2, P2, P3, and initial position has been shown as a M1, M2, M3. So, there is a need of the transformation matrix, the way we do MATLAB programming or maybe use a finite element method, same thing has been done in this case. So, what we say, the strains are calculated based on the measured displacement of the points on object surface. If we, and then there is an object and we made a number of points, maybe there is 1000 point on a surface, and then we track all the 1000 points, we will be able to find out what will be the displacement at a different point of time, and then we can really figure out what will be strain or what will be the strain rate also. So, strains are defined with a tangential plane on the surface and digital image correlation data, and it can be converted to the different triangular mesh if you are using. However, only the difference between finite element and this method is that in finite element we go with a narrow maybe smaller and smaller mesh. However, in this case it will be generally given that if the triangular size is slightly bigger, then noise level will be reduced, and that will be far better. So, that is why I say when computing strain on each triangular, smaller triangular tend to produce a noisy strain data. So, we try to keep slightly bigger data compared to finite element, and then therefore, the larger triangles are preferred for more accurate results. However, in finite element we say smaller triangles are preferred, or of course, there is always some sort of numerical limits. If lesser than that, it will give a more inaccurate result. So, we always have that limits. However, in this case slightly larger triangles are kept. Since the triangles are inherently planar, computing strain on each triangle using the same equation commonly found in a FEM method. So, we really do not really require a separate kind of algorithm. Finite element algorithms or finite element softwares can be utilized with this kind of method. By applying strain calculation on each triangle, comprehensive understanding of strain distribution and behavior across the object surface can be obtained. This is what I mentioned on this. Now, I will just take one example. You say that one of the paper which was published, and I am just trying to take one reference to that. Say surface of a rocket can be marked with a grid of the marking on that, maybe number of dots we can be keeping in the make on the rocket itself, and then we keep tracking using the DIC method. We can produce a color maps, we can use a counter plots or vector field, whichever is required. Now, if I am interested in displacement, I can make a displacement with the time, or with the velocity with the time, or this acceleration with the time. Those are possible. So, that is why I said to examine and comprehend a structural behavior, performance of the rocket under applied force, plots can be provided for the visual depiction. I will take one example of the rocket which when it hits to the stationary surface, and then we can say that to utilize this strain DIC method, we can make a number of points or the number of grid point marking on the surface of the rocket, and then we can really calculate the displacement, acceleration and velocity, and then we can plot those values, or if we are more interested we can go ahead with the color maps and then color plots, so that the better visualization can happen on the surface. So, this is I am just trying to cover. So, there is a this has been the references have been given at the bottom, and we are seeing that in this case high speed impact dynamic and deformation analysis of the target rocket system. What is a target and what is a rocket? In this case, it has been shown that if you look at this side surface, this is a stationary surface, and this is a rocket which is getting hit to surface, and this has been shown in a zoom side. We say the rocket also can be divided into 5 different tail, pre-flight, case, center and the nose. So, there are 5 different subsection in a rocket, and then we are trying to figure out what will be the response. And in this case, you can see that how this rocket is crashing, that has been plotted. Same thing, speed of the rocket, how it is varying, and it is impacting the surface, it has been shown. The same, and acceleration also has been shown of the different surfaces, the nose, center and all this. So, individually we are not fixing sensors on the rocket surface, we are making a number of dots. You are able to see the dots on the rocket and the stationary surface, and we are trying to correlate that what was happening at maybe say 0 point 1 nanosecond at surface and maybe the dot number 1, and maybe what is happening the dot 1 at the 2 nanosecond, 3 nanosecond, 4 nanosecond. So, it becomes a computationally intensive, but we are able to really diagnose without using the sensor which we believe the sensor. However, in this case camera really capturing the images, that really gives a good kind of response. So, if I try to say in this that what we have seen in image, that we are trying to capture the images of the rocket and the stationary surface, and basically what is we are trying to look at how the change in the shape is happening, the change or maybe the displacement or maybe distortion or maybe deformation of the individual dot points are happening. So, naturally if we take a many image and then we take a many data, it will becomes a computationally intensive. However, as I mentioned in the recent time, we have a good computational power available, or maybe the processors are much faster. So, this kind of method can be utilized, which was not able, we were not able to imagine this method maybe say around 5 years, 10 years back, but now that is possible, and it really gives a much faster results also. So, in this case particularly, why the rocket really gets deformed, we know it will get fired, so it is subjected to external forces. Now, when this external rocket with external forces hits the stationary surface, naturally there will be deformation. Now, there will be some assumption, we are assuming that the stationary surface will not cause any major breakage and much displacement, only in the localized zone where the rocket is getting hit will be changed. So, we really require to do this kind of testing, as I mentioned the data driven approach, which is the future, or maybe has started already, people are using this kind of method, can be utilized for that purpose. Now, I will just cover only finally one example which is published in 2020, and then they also utilize the digital image correlation technique under one compression test. So, the compression test has been shown. In this case, you are able to see the specimen, and this specimen has been enlarged and been shown over here, and in this specimen also we are able to see some sort of dots on the surface, right. And then another thing, we are able to see the 2 cameras which are capturing the images, and then cameras also capture the some distance from a specimen, it is not just attached to the specimen. Another thing, only thing is that when we are using this kind of compression testing machine, there are some sort of safety doors. So, in that situation they kept a protective panel door open, so that the cameras can really capture the images with a good resolution. And then as I mentioned the 2 cameras, and then both the cameras have been linked with this computer system, so that continuous capturing of the images happen. And then they use aluminum bar, of course, to mount this camera, that is what we say, this is an aluminum bar, and then they use some sort of a vibration isolation pad, so that there is no noise coming from the bar to the surface, and then it is on a kind of a vibration free environment. And then another thing is that in this situation also they use a kind of LED studio lights to capture the image in a proper light. As I mentioned earlier, in TT case also, that we use the good light, and so that emissions are happening properly, while in this case images which are captured are also proper. And then what they calculated, they found something like a 5 frames per second, and then each dot they take around 50 images. That means whatever the load condition they apply, and then they keep same load for the 10 seconds or maybe one more second, and then they capture the 50 images. So and then the results are fine. Now one question keeps coming in a mind, oh, camera also, if they are magnified, it can really find out what are the surface cracks, right. However, in this case they are doing a the tracking, that initially the point does not have any kind of surface crack, and after that how the crack is propagating and which level it is going. So, we see the initially no visible crack surface, and the surface crack, even whatever that they were using 5x magnification of the glass, and then they mounted, and then they used this kind of spackle pattern, random spackle pattern, and then they kept a size of 0.5 micron, which is substantially high. And then they kept this size, so that at least 9 pixels can be utilized, maybe at least this spackle is being captured by 9 pixels, so that we are able to see what kind of distortion is happening to the surface, right. And then this is the 0.5 mm LED I mentioned, the black ink, it can be, this kind of pattern can be made using the black ink or by the spraying on this. However, we know the spray will not be that kind of uniform. However, depends on the kind of the circumstances or the available resources we can utilize. So, this is the final slide of my lecture. You can see here undistorted the specimen, and then here when the load 44.5 kilonewton compression load has been applied on the surface, and then this is a strain being shown in this bar chart. We can see here the strain red means no as such strain, and then compression strain is going a reverse side. So, this is worst case kind of violet color, and then before that there is a blue color, and then green is slightly better, but in this case generally we go ahead with the red color as a major worry, but in this case the minimum worry, we are going a reverse side is the compression side. So, this is a you can see that pattern here, pattern which we are able to see red color, yellow color and greenish color. So, this zone clearly indicates that there is a possibility of failure, and that is what trying to show that initially green, then green and blue color kind of thing, and then the blue and violet color. So, that has been shown, and finally, they are able to show that there is a fracture on the surface. So, this technique is really very useful, non-contact type, and we do not really require sensor. Not only this, see otherwise what when we go with a compression test, we get this kind of example finally, right, but here they are able to track it again, but only the limitation is still is on a surface space, how it is happening, what is happening is not possible. So, naturally in a reality we require a couple of techniques together, one single technique will not be able to give complete results. So, if you are using 2-3 different techniques, so one is the confirmation, validation and complete 100% comprehensive results can be obtained when we go with the 2-3 techniques together. Thank you for attending this lecture. We will cover next lecture on selection of the techniques. We will come up with some algorithm so that it can be utilized, and then quantitatively can be selected appropriate technique for our work. Thank you.